So, let's go ahead and get to office hours. Someone can take my chair too. We have a midterm today, so I assume you all have a lot of questions.
So many.
I have like one.
Yeah.
When you do the Z diagrams and they're like the different layers of it. For the ones where it's really complicated, how do you know like how precise do the like levels of the layers? Because if it's just like 0 and then 0.5 and then 1, like, I understand it. But there's like 1 on the lab where it was like 0, and then I put like 0.2 and 0.3 because I had no idea where.
Yeah. So what you want to consider when you do that? So if I remember correctly, that was a 6-layered diagram. So you'd have like, I can't remember what it looked like, but it was 5 layers.
Yeah.
And the middle layer just had like one thing in the middle. This one had like corners. This one had like, wait, no, I got that backwards.
Yeah.
This one had dark corners and circly gray edges. And then it was like the same thing over and over again, right? So this would be like z equals 1. This would be z equals 0. This would be z equals 1. And then you just have to think about what the even split of it is. So in order to count from 0 to 1 in 1, 2, 3, 4, this would be like 0.25, 0.5, 0.75, 1. Right? And then it turns out that the 0.25 and the 0.75 are the same, and the 1 and the 0 are always the same. So we can actually label this 0, 1. And more than using the decimal points, it's easier for me to think in the decimal points. But typically for Z diagrams, we would call this 1/4 and 3/4, right? And that takes care of that one and that one. And then we call this Z equals, you can even call it 2/4 if you want, instead of 1/2. Because that gives you a nice kind of like counting, like 1 layer, 2 layer, 3 layer. Right, so we always do the fractions so it's a little bit easier to see. And I like to keep the fractions, you don't have to keep the fractions with the same denominator, but I find it easier to do the counting that way.
And so they're just like evenly spaced.
Yeah. Right, and that's the whole point of the crystal structure, is that it's got this even, like, repeating pattern, right? So it should have some even distribution. Other questions? Yeah.
This was one on one of the worksheets, and it said which IMF is the strongest: dipole, London dispersion force, ion dipole, or ion induced dipole.
So let's think about this. What are the choices?
Dipole, London dispersion force, ion dipole, and ion induced dipole.
So, this is a little bit of a tricky one. So this was one that I had on a midterm in the past, and I took off because people were like, well, we don't get this at all. But remember, most of the forces we're talking about, what's the force that we're talking about between molecules? Not IMF, but the general, like one of the fundamental forces.
Like Coulomb's force?
Coulomb force, right? So all of these, just like everything else we've really done in this class, is going to be Coulomb force dictated. So what gives rise to a stronger Coulomb force?
Higher charge.
Smaller radius.
Yeah. I'm going to switch this one to be more specific. Smaller radius is what we use when we were looking at lattice energies, but it's really shorter distance.
Okay.
And that becomes more important to think about when we start looking at molecules, because the molecules don't, like the radius of the molecule doesn't really tell us about the distance between the molecules, right? So it's really shorter distance. So when we think about this, in this case, it's really going to be the more charge, right? So how much charge does a dipole have?
A partial charge.
It has a little bit of a plus on one side, it has a little bit of a minus on the other side. A little bit of a plus on one side, a little bit of a minus on the other side. So that's where that Coulomb force happens, is this molecule slight positive, slight negative with that one. What about LDF?
No. They're not really charged.
It is a temporary kind of force. It's not really charged. It's still the Coulomb force, but it's like a temporary Coulomb force. The D, dispersion, is trying to refer to the fact that the electrons are these dynamic things that are moving. And you could accidentally, at one point in time, instead of having the electrons evenly distributed, even around something like methane, CH4, you know, there's no dipole moment. But the electrons, while they're being dynamic, could accidentally be all on one side for a moment. And that will create some very, very weak temporary attractive force. That's what the dispersion is. London was the scientist who wrote it out in a quantum mechanical. It's actually quantum mechanics is what dictates this. Ion dipole. The ion, let's go with a cation. That's going to be a full positive charge with a slight negative, slight positive. An ion-induced dipole is going to be a full positive with a very slight negative and a very slight positive, very small. Someone can take my chair and we can scoot in more. So when we think about this, which one's going to have the strongest force? Right? And there was a slide in the lectures that goes through all of the extra forces. I said there's only 3 that I really care about: London dispersion force, dipole, and hydrogen bonding. But there's like 6 or 7 other ways we can think about interactions between molecules. 6 or 7 different intermolecular forces we could talk about. And ion dipole is one of them. But they all come down to this idea of where's the charge, how far apart are they from each other? Yeah.
There was one question on worksheet 6 where phenolphthalein is pink because it holds specific wavelengths of light. It has the spectrum with the different concentrations.
So we're good on this. We can move on?
Yeah.
Good. Okay. So we're looking at phenolphthalein. We've got an absorption spectrum associated with it.
I don't know if that went back to energy of a photon, so I'd use that to find the energy. And then it asks why it's pink. And I just have to look up online said that because it changes the molecular structure.
Well, so there's a couple things happening here. So, can I see that problem real quick? I want to sketch this out. So we've got the absorption spectrum for phenolphthalein. Oh, did it go blurry? It went blurry. Hold on. Every time I erase it goes blurry, and I gotta open up this other software to control my camera. Focus. There you go. So there's the spectrum right there. There's a couple important things about this spectrum. Maybe it'll go back there. So I'm going to try my best to try and sketch this, but what we see is we've got absorbance. We've got some peak over here at like 400. We've got a valley, then we've got another peak over here at like 550. Right, and this is the absorption spectrum of phenolphthalein when it's in a pink state. Now, what's it mean? What do I mean when I say in a pink state? I mean, when we think about an indicator, we can think about a protonated version and a deprotonated version, where this one is clear, this one is pink. So if I go to this situation where I remove the H, either mostly by adding base, it's going to become pink. We could look at the chemical structure for phenolphthalein and talk about what change in chemical structure makes it become a pink compound. But when it's in this IND minus state, this charged phenolphthalein state, it absorbs here at 550. What color of light is 550? Bluish, right? Somewhere in the blue-green spectrum, right? So what color is that going to be? If it's absorbing blue-green, what color does it appear?
Red.
It's going to appear
like orange-red.
an orange-red. Turns out that the combination of red and orange in this case is going to give us that pink color.
And that little bit of red is going to give the bluish kind of green, the little bump on the left.
Yeah, so this peak over here is at 400, so that's going to be like a purple. That's going to add in some yellow. But we also have to be careful because this extra peak, depending on the spectrometer, once you get into the ultraviolet, the cuvettes and the detectors will start to hiccup a little bit. So if you remember back to your absorption spectroscopy, almost all of you had like a little hiccup in the, like once you got to like 400, once you get past like the 430 mark, it becomes unreliable because of the instruments we're using. If we spend another $2,000 on each of those, maybe we could get something that goes out a bit further. But since we have 64, then another 48. Since we have like 100 of those, 150 of those, an extra $2,000. Oh, let's make space. So that's what it meant for why it was appearing pink. I wanted you to think about the physical properties of the absorption spectrum.
Okay, wasn't anything on acid-base reactions?
No, you know, it was just if it's in the pink state, why does it have that pink color? So this is one of those things where people have been asking like, oh, is the exam cumulative? And I'm like, no-ish. Because almost everything we learned in the first 6 weeks can relate to the stuff we're learning now. So it all comes back in one way or another. There are some things that definitely aren't coming back yet, but we will come back. The final is cumulative. Other questions?
Yeah, on over to 6. We do, can we do number 11?
Sure. What is number 11?
Acetic acid reacts with sodium carbonate to produce sodium acetate.
Okay. Acetic acid reacts with sodium
Carbonate to produce sodium acetate, carbon dioxide, and water. It says how many milliliters of 0.054 molar acetic acid solution is required to completely react 100 grams of sodium carbonate.
So we're looking at this, right? So we have to remember a couple things. One, carbonate reaction. That's one of our typical reactions that we should remember. This is something that I wrote down on the board. Was on the quiz as well. Carbonates react if you form carbonic acid, unless you're doing something special to that situation, keeping it under pressure, keeping it at cold temperatures. The carbonic acid breaks down into CO2 and H2O. This is part of how soda companies actually carbonate their sodas. Rather than using like an airstream on every bottle and sealing it, they actually pour liquid carbonic acid and then seal it. And the carbonic acid decomposes into CO2. There's also an equilibrium of CO2 with water that can go back to forming carbonic acid. You'll learn about that more in 125. That's what's acidifying the oceans. CO2 absorbs into water and can then become carbonic acid again. So, what we've got here, first thing we have to do, we write down the chemical reaction, which I've got wrong because I need my states of matter. That's aqueous. This is solid. This is aqueous. This is gas. This is liquid. Always states of matter if we want the chemical reaction to be correct. What's the other thing that's missing? Yeah, we have to balance the chemical reaction. I'm pretty comfortable with this one because I know I need 2 H's to form carbonic acid, and carbonic acid becomes CO2 and H2O, so I need 2 of those. And that works out nicely because now I can balance my 2 sodiums and my 2 acetate anions. Now, we can think about this in terms of the full stoichiometry. Why is this thing squeaking so much? Oh, it's gonna drive me crazy. Better. Okay. So we have to think about this now. The thing is, we don't know. Was it 0.054 or 0.54?
0.054 molar.
0.054 molarity. Cool. So we need to, for our starting step, we need to get the moles of each thing. So I've got volume times 0.054. The mass of sodium carbonate is something like 106 or 130 something. I need help for that one. Calculators, periodic tables, internet, whatever you want, just look it up real quick. You've got a thing there. Can you just like
Like the mass of what?
sodium carbonate? Why am I looking for the molar mass of sodium
Do
carbonate?
you know what the recipe for moles? Do you know what sodium is?
23.
Uh,
Carbon is 12, oxygen is 16, so 23 times 2 plus 12 plus 16 times 3. I just can't do
You wanna
that.
say that
wait,
again slower.
60 plus 46. I think it's a 103.
I think it's 103.
It's 106.
106.
Oh yeah, yeah, it's 106. It's
Yeah,
what? Yeah,
106.
because
Great.
sodium.
I know it's something like that. Okay, so 100 is going to be, let me think about this. I'm going to have 1 mole for 106 grams, right? This conversion factor, or this conversion property, the molecular weight's going to let me turn this grams into a moles. 100 divided by 106 is going to be about 1. Let's call it 0.98. Someone with a calculator give me the real number. Because it's 100 divided by 106, it should be something about, like if it was 100 divided by 100, it'd be 1. 100 divided by 106 should be a little bit less than 1.
Probably a little bit smaller.
94.
0.94. Now, there's an important key term in this problem that tells us how we're going to do this. Because right now, with an unknown here, I can't determine the limiting reactant, so I can't do my reaction step. However, the problem says find the volume of acetic acid that will completely react. So that is code for at my end step, I want zeros for both of these.
Okay.
Now, I say if there's a 0, both are limiting, right? So this one is limiting because there's 0 left over at the end. This one is also limiting because there's 0 left over at the end, right? So that means either one works for me to do my reaction step because both are going to limit either way. So I'm going to go ahead and do the 0.94 because I think it's going to make my math work out a little bit better. So I'm going to have minus 0.94, minus 0.94, plus 0.94, plus 0.94, plus 0.94. Notice everything over here doesn't really matter, but still I'm going to make sure I do this all correctly. I'm going to include my mole ratio. This is 0.94, and I've got 2 moles of acetic acid for every 1 mole of this. Right, so it's a 2-to-1 ratio. The thing that I want to talk about goes on top. My limiting reactant goes on bottom. This one, we don't technically have to do a mole ratio for the limiting reactant, but I like to put it on everything just to make sure I don't forget. This is a 2-to-1. This is a 1-to-1. This is a 1-to-1. This 1-to-1 doesn't actually matter because you're converting from sodium carbonate to sodium carbonate. This 1-to-1 does matter because you're converting from sodium carbonate to carbon dioxide. So even though
scored, like if we don't put 1-to-1,
if it's a 1-to-1 ratio, technically you should still have the unit conversion, right? Because moles of carbon dioxide plus moles of sodium carbonate doesn't make sense. But moles of carbon dioxide plus, the conversion factor, so it's plus moles of carbon dioxide does make sense. Now, for this problem, you wouldn't get marked off because you don't even need that to do the problem, right? Here's my entire equation that I need right here. I've got 0.054V minus can I do math in my head? 1.88. 0.94 times 2 is equal to 0. Solve for V. Right? Because we have that statement of completely react or equally react, we know that the moles, and the other way, we could have done this without doing the whole table and all of this, because essentially that statement tells us this amount of moles has to equal this amount of moles. And you notice with the mole ratio in there. So when I subtract over, I've got this amount of moles equal to this amount of moles, plus the mole ratio. That'll give me my volume. In what units?
Milliliters. Well, it says milliliters in this problem.
Right, but if I do this
Oh, liters.
division,
It'll be
it's going to be in
liters.
liters because that 0.054 is moles per liter.
And then you just convert it. To
And then you
milliliters.
convert.
Cool.
So this is a pretty great example of a straightforward stoichiometry problem that's related to things we've done before. Brings back the idea of molarity, brings back molecular weight, some simple definitions of what happens to limiting reactant and process reactant. It's a great problem. Like, your final is going to have like 5 of these. For sure. Stoichiometry, writing reactions, and then understanding how to do reactions is like...
So our midterm's gonna have like 1 or 2.
That would make sense.
Yeah.
I'm not saying yes, but I'm not saying no. Does that clear it up? Was it just that one like conceptual idea of how you get to a 0?
Yeah.
So this is something that has not been a big theme in Chem 124 yet. It's been a minor theme, but key terms giving us clues as to what problems we're doing. Right? Everything like everything on the first midterm really had terms that were specific to the equations or the calculations that we were doing. So you didn't have to look for extra hints. Since everything we've been dealing with is chemical compounds, interactions, and like chemical reactions, we have to get a little bit more nuanced and start looking for those special terms that tell us what's going on. Another one that we might use is how much acetic acid, what volume of acetic acid would I need for acetic acid to be in excess? Right? That term tells us, or the other thing we'll do is like combust methane with excess oxygen, right? That word excess is telling us which the limiting reactant is. Because if one is in excess, the other is automatically limited. So that's another key term we might want to be on the lookout for. We're also going to be doing a lot more balancing reactions and stoichiometry once we get back after the week off. Other questions? Yeah.
Do we need to show our work like this in a table like
No.
this?
Right? No. This is just the way the organization makes most sense to me for a couple reasons. One, it keeps all of my information contained in like a single column for each reactant and each product. Two, since I also teach Chem 129 where we're doing equilibrium tables, so this is a stoichiometry table. And 120.
Equilibrium ones are the same.
Yeah. Equilibrium tables are the same-ish. There's a couple important differences. When you're talking about chemical equilibrium, you'll get into that in Chem 125. But you essentially need to put it in a table like this for it to make sense when you're doing equilibrium tables.
Oh, okay. I was like, yeah.
Okay. When you're doing equilibrium tables, you need to do it this way. So I try to get people thinking about this kind of tabular form of doing stoichiometry early.
Okay.
Other questions?
I'm the one from worksheet 60, and this is more of the hybridization geometry.
Yeah.
And it's like CH, it's just a big molecule.
Yeah.
If you wanted to just look at it.
That is, wait, hold that up again. That is that 2 methyl groups? So that is not toluene, that is
xylene.
Xylene, yes.
Is this on the like the xylene sort of problem? Is that on the team? I was gonna ask the Rydberg problem, but I know that's not gonna be on there.
The Rydberg question, I cannot think of anything that we have done since the first midterm that would bring Rydberg back for the second midterm.
Okay.
Thinking, no, I can't think of anything, but you definitely need it for the final. So this one, if I remember correctly, it does the ortho version of xylene. You don't need to know that part. So there's essentially 3 different isomers of xylene. There's what we call There's this one where the two methyl groups are next to each other. There's one where the methyl groups are have something in between them. And there's one where the methyl groups are directly away from each other. So this is like the ortho, the meta, and the para, if I can remember organic chemistry.
Wait, what?
So you don't need to know that part. I'm giving you extra information that's not really critical to the problem. The thing that we need to know is that this is xylene. It gives you the molecular structure. It gives you this structure. We have to realize that this is the shorthand notation. If I wanted to write this out explicitly, I'd have a carbon, 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 a carbon. Bond, bond, bond. This is going to have a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen, a hydrogen. This one's going to have a hydrogen. This one's going to have a hydrogen. This one's going to have a hydrogen. A hydrogen. Right, so I take every vertex, every line ending, and I say there's a carbon there. And then with every vertex, every line, and well, with every carbon, I optimize the number of hydrogens. Yeah, you can just put that on your desk.
Sorry.
Yeah. You want to just put the maximum number of hydrogens necessary, or the minimum number of hydrogens necessary to get carbon with 4 bonds on each. And then the question is, what's the hybridization and structure of every carbon in this? That's going to be 8 carbons. Now, I'm going to cheat a little bit. Notice all of those carbons are going to have the same, right? 1, 2, double, 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 1, 2, double. All of those carbons inside the ring have the same bonding pattern, which means they're going to have the same orbital hybridization and the same molecular geometry. If you have 3 things attached, what's your geometry?
Trigonal planar.
And if you're trigonal planar, what's your orbital hybridization?
SP2.
Yeah.
Does the orbital hybridization include lone pairs?
Yes.
Okay.
We don't have any lone pairs in this case,
Yeah,
but it does include lone pairs. So the orbital hybridization is essentially looking at, and we did this pretty quick, because
similar to the electron geometry.
Yeah, similar to the electron geometry. We could have done this the backwards way of saying I've got 1, 2, 3 electron groups, so I'm going to need 3 hybrid orbitals. That's going to be an sp2 hybrid. The leftover p orbital is what gives rise to the double bonds everywhere.
Mm-hmm.
Now, these compounds, these benzene ring-like compounds, also have some really interesting physical properties that we can get into, which is to say, resonance structure. Right? There's no preference for where the double bonds are. We will often write this if we wanted to average the 2 together. It's a little weird looking right now, but if we wanted to average the 2 together, do it like that. And the really interesting thing about benzene ring structures is if you put it in a magnetic field, the electrons can actually run in a full ring, and you get what's called ring current. And these become like little induced magnetic fields. It's really neat. You don't need any of that information for this problem. It's just really neat. And the reason that can happen is because of the unhybridized p orbital left over here. That's going to be sticking in and out of the plane that gives space for the electrons to kind of run in circles. Yeah?
What would be the overall geometry of this?
Right, so let's go ahead and finish this real quick. These 2 carbons also have the same. What's their geometry? What's their hybridization? sp3. Those shouldn't be capital S's, by the way. Those should be lowercase s's. I'm just getting carried away. sp3. So when we look at this thing, we've got essentially, I don't have what I need to build it right now. But essentially, you notice this whole body of it is flat, right? It's all trigonal planar. That's going to be one big flat thing with these two wiggly things poking off of it. So overall, you would say, look, the majority of this structure is trigonal planar, so you're going to have a planar molecule. That becomes really important because planar molecules can essentially slide in between other structures. Xylenes, toluenes, other things like this. Nicotine actually also has a benzene ring-like structure inside of it. All of those things can actually fit in between DNA strands. Because they're flat, they can fit in between base pairs and inside strands, and they create hiccups when you're replicating DNA, which is part of how they damage cells, and like that's part of how nicotine causes cancer and all that.
Oh wait, that's
Yeah, so that's extra information with the fact that we've got this overall flat structure. Does have physical importance to it. Yeah.
With the sp bonds, I thought the S stands for sigma and the P stands for pi bonds, right?
No. That is an s orbital and a p orbital. So if we wanted to count the sigma bonds and pi bonds in this structure, we have to remember another thing. I don't know why I'm changing colors so much. I'm changing colors again. A single bond is a sigma. A double bond is a sigma and a pi. A triple bond is a sigma plus a pi plus a pi. So S and P are the atomic orbital designations. So that's the L equals 0, L equals 1.
Yeah.
S orbital is that. P orbital is that. Not drawn very well, but you get the idea. Right? So that's the S orbital, that's the P orbital. When I create an sp hybrid, I'm putting these two orbitals on the same atom together to make a new geometry on that atom.
Could you sketch an sp2 to sp3?
I could try. sp2 I can sketch. So when we look at sp2, we're essentially taking an s orbital plus a p orbital plus a p orbital, recognizing that these also have some phase associated with them. If I'm adding three things together, I need to be getting three orbitals back out. And the way that the addition works is I end up getting an I get an sp2 hybrid like that, an sp2 hybrid like that, an sp2 hybrid like that. The pictures in the book are way better than the pictures I can draw. But if we put all three of these together, we end up getting something that looks kind of like this.
do the hybrid orbitals like individually have phase?
Yeah, like these individually have phase as well, probably something like that.
But we have to like at what level of detail will we have to know how to hybridize the orbitals?
This level.
Right.
Right. I was specifically asked, I've never asked you to sketch hybrid orbitals.
Okay.
But I was asked to sketch them. So this is like how the sketch happens. And to be clear, what you're doing with these pictures is solving a combination of differential equations and integrals. Right?
So that's why it's
So,
stupid.
yeah. So remember, these orbitals, these atomic orbitals came from solving the Schrödinger equation, which was the second order differential equation, and then taking the integral of the wave function squared. So like getting the wave function, which gave us these different shapes, was solving a second order differential equation, and then getting the probability distributions from those wave functions was doing an integral. And then we say, look, if this is a solution, and this is a solution, then this plus this is also a solution. That works out in experience with differential equations 1 through 5. Oh, great. So you know a linear combination of solutions is a solution. Linear combinations of solutions is a new set of solutions. That's all we're doing. So you can have it where it's like this plus this plus this, or this minus this minus this, or this plus this minus this, and you get different linear combinations that give you solutions to the single atom. Turns out when we go to molecular orbital theory in Chem 126, which I don't think any of you are taking, but when you go to molecular orbital theory, you do the same thing, but instead of restricting yourself to a single atom, you do this over the entire molecule. So if we could get a molecular orbital for this xylene, by saying, look, I've got 1s, 2s, 2p on every carbon and a 1s on every hydrogen. If I add all of those together in different combinatory ways, I'm going to get some wave function that describes the electron distribution over the entire molecule. I'm going to get some energy levels that tell me about the interactions of that molecule with thermal energy or photonic energy or kinetic energy. Right? And we're not going that far, but that's where hybrid orbital to molecular orbital to understanding molecules could go. That's also the stuff that I really like to do.
That's cool.
I'm just confused on how you know there's an S or a P orbital.
How do you know if it's an S or a P orbital?
Yeah, because I'm just looking at I'm just looking at carbons and hydrogens, and I don't see how.
Okay, so for carbons and hydrogens, if we think about a carbon, what's the electron configuration for carbon?
1s2, 2s2, 2p6, and 2p2.
There you go, yeah. 1s2, 2s2, 2p2. That's the electron configuration for carbon. So each of those carbons has an S, an S, and a P. Right? So we're really just going to be concerned with those outermost electrons, those valence shell electrons. So we're going to be really concerned about the 2s, 2p. And that's where these S's and P's come from. So this is on a carbon, this is the 2s, this is the 2p. And we say rather than thinking about it in terms of an atom, because it's no longer just a single atom, right? It's interacting with other things.
Yeah.
I'm going to think about it. I don't want to go to the point of doing all of the atoms in the molecule. I want to have some sort of in-between where I'm not doing full molecular orbital theory, which would be the right thing to do. But I'm definitely more complicated than single atoms. If I only had something that was like somewhere in between those two, that was like a combination of atomic theory and like that's hybrid orbital theory. Is that kind of, well, it's not MO theory, but it gets us pretty quick answers. Right? That's hybrid orbital theory. Now, hybrid orbital theory has this big, enormous flaw in it, which is you need a priori information in order to determine the hybridization, which is to say you need information in order to get information, right? I can't just say, what's the hybridization of a carbon? It's like, could be any number of things. What's the hybridization of an oxygen? We could have hybridization of oxygens. Could be any number of things. I need more information. And this is one of the tragedies, one of the reasons I don't like hybrid orbital theory. In order to get correct orbital hybridization, you need to know the geometry. So hybrid orbital theory, because why did I do an S with 2 P's instead of an S with 3 P's, or an S with a P, or why didn't I bring in those D orbitals that are later on, or like why didn't I bring in some other orbital combination? And the answer is, we do this hybrid orbital so we get the correct geometry that we already know is there.
So you use the geometry to find the
hybridization.
Okay.
Yeah, and which is also why you can also use the bond count to get the hybridization, because the bond count gives us geometry, the geometry gives us hybridization, so we get this nice little like cyclic. As long as I have one of those 3 pieces of information, I can figure out the other 2. So it's like bonding, right? As long as I've got one of those 3 pieces of information, I can figure out the others. And you get this nice little circle of like, and you can also, well, I don't know, you can't go across, there's only 3 things. So if I had, and it's not specific directional, right? I can go either way. If I have the hybridization, I can get the geometry or the bonding. If I have the bonding, I can get the geometry or the hybridization. The nice thing that hybridization does, that Vesper totally, because keep in mind, Vesper valence shell electron pair repulsion is completely classical. Totally doesn't. It gets the geometry right, and that's it. It can't explain any of the other phenomena we see. So Vesper does not explain how pi bonds work or how double bonds work. It's just like, oh, it's like 4 electrons. That's just in a group of electrons that's going to cause repulsion. Just like, shouldn't 4 electrons cause more repulsion than 2? Shouldn't that like change? Nope. That's because Vesper is trying to treat quantum mechanical objects in this classical kind of way. Hybrid orbital theory is a step better than Vesper. So hybrid orbital theory is what gives us that leftover p orbital. So if you look at the trigonal planar, look at any one of those carbons in the blue box. You've got your sp hybrid, so you can see the geometry of each of those carbons is going to be at 120 degrees. You're going to have 3 sigma bonds because I've got 1, 2, 3 orbitals that can directly overlap. And then I've also, and I apologize for my drawing, but I've also got an unhybridized. That is coming in and out of the board. Just pretend like I can draw 3-dimensionally. There's this unhybridized p orbital sitting there as well. That's what gives rise to the pi bond. And each of these carbons has this unhybridized p orbital sitting here, which gives rise to the resonance structure where you can have this thing kind of like run in a circle.
Can I take a look at it?
Yeah. I just made a mess of that picture.
Yeah.
But that's the extra thing that hybrid orbital theory does that Vesper does not do. Give me just a second.
Can I blow my nose? Do that talk thing?
Yeah, I can do
Yeah,
you
I actually
one
just-
better.
That's-
Yeah. Okay. Other questions about this? Trash cans behind the door. So I'm going to go ahead and I'm going to erase this for now. I'm going to let you all take a moment and figure out what other questions you have. I'm going to set this person up to take. See how my.
So, what other questions? I want to do some more stoichiometry. I want to do 12. 12 is a good problem to go over. Carbon disulfide, a liquid, it gives you the formula that you need to find the maximum amount of carbon disulfide produced out of this and that. How many grams of each reactor remain, percentage yield.
Oh wait, what was the one naming problem we were going over and we got like 2
Oh,
answers?
it's dicesium. Dicesium sulfide?
Something like that.
CS2S?
Yeah, CS2S, what is it? I said cesium sulfide.
Yeah, you said cesium sulfide, I said dicesium. I think it's.
Because isn't that ionic? So
Yeah,
you just say cesium
That's what we were. That's
I
what
think
it
it's
was.
cesium sulfide.
But
'cause you
everything
don't-
on the internet it all said dicesium sulfide.
Every single
which
thing.
is weird.
We typed in dicesium sulfide, CS2S. Typed in CS2S, dicesium sulfide.
That's hella weird. Then.
I know.
Yeah,
that's
that'd
why
be a
I
good
was,
question.
unless it's some kind of weird rule.
Yeah.
But we don't know. So,
Okay, let's see. I forgot an equation sheet.
He doesn't need one.
Probably not, to be honest.
He'll be fine. Oh, really?
I mean,
Oh, yeah, that makes sense.
Like, think of how many equations we've had. Like, I put a periodic table on the screen. Oh, I guess the solubility rule, right?
Yep.
Yes. Yeah, we don't use many equations.
Yeah.
That sucks.
so that means no packing efficiency.
So, what other questions do y'all have?
Oh, this is a quick one, but
Sure.
would you name cesium 2 at like S like so? Would you name that cesium sulfide or dicesium sulfide? 'Cause-
Cesium sulfide.
So that's what we thought, but then everywhere you look up on the internet, it says dicesium sulfide.
Really?
Yeah, which is weird because it's
Dicesium
ionic, right? So you would
Yeah.
name it cesium sulfide.
So, It could be one of those funny things.
It's just like an irregularity.
Mm-hmm.
Okay. But for the most part, ionic would be just like
Well, so what I mean by one of those funny things is like calling CH3COOH acetic acid,
yeah.
right? It should be called ethanoic acid. That's the proper international name for it. But it has this common scientific name that everybody uses. It could be that dicesium sulfide caught on in like the 1800s or something like that, and everyone just started using that. And so it has this common scientific name, but the international name, I would just say cesium sulfide.
Okay.
Right? The dye, no, someone can come in and take that seat.
Oh, sweet.
The dye is redundant, right? I already know it's sulfide. I already know that there's going to be 2 + 1 charges to balance that -2 charge.
Okay.
So saying that, and for me, it comes down to the same thing that's important to me about figures in graphs, is I don't want redundant information. Like, if you name your, like, pet peeve, just because I haven't written anything on the board in a while, if you named this, let's see, what's something that we plot? Let's do natural log of k. This is something from a different class versus 1/t. This is a Chem 125 plot you'll do in the future. If you do natural log of k versus, if you call this natural log of k versus 1/t, I'm like, no, that's wrong. And you're like, oh, that's because it's supposed to be 1/t. But I know, like, this is, I already have that information, right? The axes are labeled. I've got that information. This is redundant. This is not telling me anything new. It's a terrible title. It's the mathematically correct title. Come on in. It's the mathematically correct title of like the independent variable versus dependent variable, or however that's supposed to go. But in a science class, that information is all redundant and kind of useless. Yeah. Yeah. Where did I put those things? I think it's in this pile. Last name?
Houston.
What was that name?
Houston.
There we go.
Thank you.
You're welcome. Okay. Other questions?
Another stoichiometry question.
Yeah.
On it's number 12 on homework 6. It says carbon disulfide is a liquid that is used in the production of rayon and cellophane. It is manufactured from methane and elemental sulfur via the following reaction, which is CH4 plus 4S yields CS2 plus 2H2S.
You said CH4 plus 4S
Correct.
goes to
CS2 plus 2H2S.
wow. That's a weird reaction.
Yeah. And then the first question.
And it was just 4S. It wasn't like SH or anything like that.
No.
Weird.
The sulfur not exist usually by itself.
No, so there's actually there's 2 or 3 different styles of sulfur. Typically natural sulfur exists as an S4 or S8.
Okay.
So they exist in these kind of like clusters, and that has to do with like just the way that they interact with each other, the d orbitals, the electronegativities, stuff like that. But we'll just go with the way the chemical reaction was written down. We'll work from here.
And the first question is, what is the maximum of carbon disulfide that can be produced from 400 grams of methane and 200 grams of sulfur? So is that when you just convert to moles and then find a limiting reactant and just subtract?
Yeah. So we know we're starting with zeros here. We don't really care about the H2S, and I forgot to put states. This is a gas, but we can still measure it in sulfur. Does it say whether the sulfur? Does it give states of matter on there?
Carbon disulfide is a liquid, and it does not say whether or not the sulfur is anything. So
Let's go with solid sulfur. Sulfur is usually a powder. CH4 is usually a gas.
yes,
So-
CH4 is a gas.
So we can, and I'm guessing the hydrosulfuric, or sorry, hydrosulfuric acid, no, H2S. Why can't I name that right now? And 129 students are going to be shocked. I hope they don't watch this. Oh, it is hydrosulfuric acid. Just like hydrochloric. Yeah. I was just getting hydrosulfuric and sulfuric are very different things, and I was messing with my brain for a minute.
HS is HS is the hydrosulfuric, or
H2S is hydrosulfuric acid.
so what's HS?
HS would be HS minus,
Mhm.
and that would be the monoprotic hydrosulfuric acid, or hydrogen sulfide, or the monobasic hydrogen sulfuric acid, hydrosulfuric acid. There's a bunch of different ways you can name it, depending on what you're trying to communicate. So we're going to do 400 divided by 18, and we're going to do 200 divided by, what's the molecular weight of sulfur, like 32?
Sulfur is, yeah, 32.
200 divided by 32, that will get us our moles of each. I'm going to call that about 20, so that's going to be like 10 moles of CH4, a little bit more than that. Sorry,
No, that'd be
20. Let's say 22, since it's 18 and not actually 20. Approximate math. Calculators, though, help me out. You're like not going to calculate anything. Trust everyone else. It's fine. 200 divided by 32, that one I cannot do in my head. I'll say that's a third of 20.
6.25.
This one is 6.25?
Yeah.
Is this one actually 22?
It's 22.22.
Cool. Okay, so we look at this and we say, great, clearly 6.25 is limiting. Why is that clearly limiting? One, there's less of it, which is a good hint, but also I need 4 times more sulfur than methane for this reaction to react, for this reaction to be balanced. I've got less sulfur than methane.
Right.
This would have been much more interesting if I switched to the 400 and the 200.
Yeah.
And it would have been like, oh, which one is actually limiting? Would have made you think a little bit. Yeah.
Should it be 18 or 16? Because isn't carbon?
Oh, you're right, it's 16. I did what? Wait, yeah, it's 16. I did water instead of methane.
25.
25 point something?
Just 25.
Yeah, it's just 25.
Okay. So, still, clearly, this 6.25 is limiting, so I'm going to have minus 6.25 minus 6.25 plus 6.25 plus 6.25. Okay, need my mole ratios in there to get this right, so I'm going to have a 1 to 4. Notice everything, well, let's just do them. This is going to have 4 to 4. This is going to have 1 to 4. And this is going to have 2 to 4. Right? The thing I'm switching to divided by the limiting reactance coefficient every time. Then I can go ahead and do my math for all of these. This one is, of course, 0. That's part of what makes it the limiting reactant. Then something I might have forgot to mention is you can kind of guess and check. Like if we guessed the wrong thing, we would have gotten a negative amount of material left, which is nonsense, which means we made a bad choice and we should go back and redo the problem with the other thing as our choice. But we're better off just making the right choice the first time. So 6.25 divided by 25, it doesn't matter, right? All that matters is the number here because the problem's asking us how much carbon sulfide, is it carbon disulfide? Yeah, carbon disulfide we can make given these amounts. So 6.25 divided by 4.
1.5625. So it's 1.56.
Yeah, let's go with 1.56. 1.56 moles. Done. Does it ask for specific units for your answer?
It does not. It's
Then go with moles. So
it's a 3-part question.
my rule of thumb is if I don't ask you, because it should ask you for specific units. It should ask you for your answer in moles, or your answer in grams, or your answer in liters if it's gas, or liters if it's a liquid, or milliliters. If I don't give you a specific a particular unit I wanted in, go with the easiest one to calculate. Right? Moles is the easiest one to calculate. I cannot take points away if I didn't tell you what units to put it in. Right? Moles, like, please don't put it into some weird unit. Technically, I still can't take points off, but like, I'll be frustrated. But just make it easy for yourself. If I'm not specific, go with the easiest thing to calculate.
Put it in pounds.
You would.
And then in
And both those things would still technically be correct, and I would roll my eyes and then have to do an extra calculation to check your work. But you'd still get credit, because it's still correct.
And there's a C part to this, and this
Mhm.
is, what is the percent yield if the actual yield of carbon disulfide is 95.8 grams?
So let's go ahead now for this part. Let's figure out how many grams we have here. So that's 6476. Where did I get that 76?
More mass.
More mass.
Molar mass. 12 plus 32 plus 32. I can't do that in my head. It's going to be like 10 something.
118.56.
So, now here's what this problem is getting at. And this kind of gets back to what we did when we were looking at the thermite reaction, when we were looking at the hydrogen balloons, when we were looking at reality versus on paper, right? So, on paper, this reaction happens perfectly. Everything does exactly what it's supposed to. The reaction goes to completion. There's no equilibrium or anything. Reaction just happens, right? We don't know anything about how fast this reaction happens. We have no idea about the energetics, whether this is exothermic giving off heat or endothermic taking up heat. No idea. But when a couple folks went into a laboratory and actually did this experiment a couple hundred times, they were like, look, I only get 95.8 grams from this. I don't get 118. So that means the amount that you actually make is different from the amount that you theoretically make. So in order to calculate this, we go through the calculation. This is in chapter 1 or 2. And we've looked at it before, but it's been weeks and weeks since we've looked at it, right? So I'm going to have 118.56 minus 95.8. That's going to get me absolute value. That's going to get me how far off from the theoretical yield I am. And then I'm going to divide by the 118.56. This will give me essentially a ratio of how far off I am from what I should theoretically make. And then if I multiply it by 100, that will give me my percent. Right? And that will tell me how much I made. Yeah.
Isn't that percent error?
Yeah.
I don't think that's percent.
Oh,
error.
you
That's
are
percent
so
error.
right. Percent yield, yeah, I did percent error. Percent yield's even easier.
Yeah, you just divide.
Yeah, you just have how much you started with, right? You have the ratio of how much you made versus how much you should have made. Way easier. So getting the percent error would be the missing yield, right? Which is actually kind of more useful. But this will give us a percent yield. What I had before was a percent error, or like the amount that was missing. Is it possible to have a percent yield over 100%?
Yeah.
It
Like reacts to something.
if you're doing it out in the open air, and
Yeah.
there's technically other things interacting.
Yeah.
With the
So
system.
we can actually, so on paper, it's impossible to get a percent yield over 100%. We should never make more than what we have. But almost always in nature, whenever you get a percent yield above 100%, which happens all the time when you're doing experiments, is because of contamination. Some extra thing that got into your reaction that you were not expecting. That extra thing that gets into your reaction makes it look like you made more stuff, but it's just because you've got some extra junk in there that you didn't take into account. So if you get a percent yield over 100%, you're like, that just means I got junk I didn't want.
Is that kind of like combustion, or like you like produce things you don't usually?
Yeah, exactly. Like combustion. Because all the combustions we do on paper are all oxygen reactions, all complete combustions. You know, In actual combustion, you're going to be making nitrogen monoxide, nitrogen dioxide. You're going to be making sulfur dioxide, all of these other things because of the components in the fuel, and the air that you're burning with is not pure oxygen. It's a combination of oxygen, nitrogen, a couple other things. I got to answer a question in the hallway real quick. All of you find another problem you want me to work on.
19B. Does anyone else have trouble with that one?
Is that on homework 6?
Oh yeah.
Could you go over 10 off?
Oh yeah, I like that. That's a good one to ask.
Which section? Which camera are you in?
What came I in?
Yeah.
Most of them.
Okay. This one.
Alright.
What are we doing?
Are you guys all fine if we do it? Okay, 19B. It's the molarity of a solution. Okay, molarity of a solution containing 7.25 milligrams of calcium chloride per milliliter of solution.
Whoa, okay. So, we've got how much?
7.25 milligrams of calcium chloride.
Per milliliter?
Yeah, of solution.
And we want to do some operation that gets us to moles per liter. Because moles per liter is concentration.
Yeah.
Right, so as soon as we identify that, is it that tricky?
Wait, what just happened? Sorry. So, don't you just convert to moles, right?
Yeah.
Milligrams to moles, and you just leave it as milliliters over?
Well, we're going to convert this to liters as well.
Okay.
Because moles per
Oh.
liter would be concentration.
Wait, doesn't it say per milliliters?
What's the question say again?
Molarity of a solution containing 7.25 milligrams of calcium chloride per milliliter of solution.
Yes. So that is how much it's containing, but concentration is always in moles per liter.
So it wants us to find the molarity?
Yeah.
And then it gives us that?
Yeah.
That's, okay. That's not that obvious, is it?
I don't know.
it,
I mean, it is to me, but I kind of do this a lot.
it just seemed like the question was phrased weirdly.
It could be. It sounds like
Okay.
a pretty weird.
Would you just like convert it into like standard units like grams and liters?
Yeah.
And
So first thing to realize is 7.25 milligrams is 7.25 times 10 to the minus 3 grams, and a milliliter is 1 times 10 to the minus 3 liters. I can get rid of my 10s to the minus 3s. So I've got 7.25 grams per liter. Then I can just multiply by 1 over my molecular weight. Chlorine is 35 each, so that's going to be 70. Calcium is, I can't remember, 40. So that's going to be 70 plus 40 is 110. So that's going to be 7.25 divided by a little bit more than 100 is going to be 0.00725 or 0.006. 6 times 10 to the minus 3? I'm just doing that in my head. Is probably what do
I
you?
just got 0.065 more.
Oh, am I off by an extra? Oh, I'm off by an extra digit. 0.065 moles per liter. I rounded too much. This is a 6.5 times 10 to the minus 2 is the same as 0.065. Right? That's all it was asking us to do. But notice, this is something I mentioned before you got into office hours. These questions, now that we're getting into this more like nuanced treatment of chemicals, we really need to be much more careful with our reading, and we need to be looking for those key terms that tell us kind of what math we're supposed to be doing.
Mine's really quick. Can you just like quickly run through the sigmas and pi's in the single, triple, and double bonds?
Yeah. So I had that down here just a moment ago. That's it.
Thank you.
I just have a quick question too. Would PF4 minus 3 be, would that have a permanent dipole moment or not?
PF4.
PO4.
Oh, PO4. It's like PF4 minus C. Let's think about that. Where did I put my black marker? How do I
You
do?
dropped it.
Oh, thank you. So we need to draw the Lewis structure for it. I think it's going to be something like that.
Yeah.
Does everyone agree? See a lot of nods. I should put my...
And then wouldn't it be tetrahedral since it's a resonance structure?
Uh-huh.
And then
Well, it's tetrahedral because it has 4 electron groups attached. So, does it have a permanent dipole if it's tetrahedral?
Yeah.
No.
Why not?
Because it's still symmetrical.
Still symmetrical, but what about these minuses over here?
I don't know if they matter because the resonance.
Yeah, that's right. So these minuses don't actually matter because I should have 4 resonance structures averaged together. The -3 is actually distributed over the entire thing. I'm doing a bad job when I draw my Lewis structure. I'm essentially doing a bad job representing the fact that electrons are dynamic objects. Right? So this double bond could be at any one of these 4 spots, and it's actually the actual structure is going to be an average of those 4 things. Yeah.
Is there any case where like the formal charge would affect, like even if say the geometry was symmetrical, is there any case where the formal charge will make it have a permanent dipole?
Not really, because any case where you have a formal charge calculation, you probably also have resonance structures. I'm not going to say 100% that's true, but every situation we've looked at in class so far where we do a formal charge, we're like, oh, this thing's minus. We've also had a resonance structure where that minus could move around because electrons are dynamic. Let's all scoot in a little bit more. Let's get some more people in here. There's space on the floor here. When it gets to being like 4 people in the hallway, I start to feel bad. Someone can sit on the desk there if they're comfortable with that.
Wouldn't the double bond be a little bit shorter, but since it's a resonance structure, it doesn't matter?
Yeah,
Can I just say no?
technically,
Yeah, for sure.
technically, right, so when we draw the Lewis structure, we're like double bond, single bond, single bond, single bond. Part of the reason we need to go to resonance structures is because that idea of the double bond is shorter works fine when there's not a resonance structure. But when there's a resonance structure, each of these bonds is part-time double, part-time single. How often? This one is, 3/4 of the time is a double bond, is a single bond, and 1/4 of the time is a double bond. So we can essentially do 2 times 1/4 plus 3 times 3/4. Wait, no, 1 times 3/4. That's going to be 2 5/4. Each of these bonds would actually be like a 1 1/4 bond, right? Because of that shared resonance structure. In all actuality, what we should do is get away from Lewis structures and that idea of bonds and go to molecular orbital theory, but that's for 126. But we can still do those types of approximations. So no dipole moment. It's symmetric and has a resonance structure. Other questions?
Didn't you want to do 20?
Or, I just had a question on number 10. It talks about the concentration of ions in solution. So, like, we have to do to find out how much of each, like, the reactant we have and how much product is made. And then it's asking for the concentration of ions of NH4NO3. And I ended up with 1.4 grams.
So let's get some context.
Yeah.
What is the what's the chemical reaction we're looking at?
Ammonium carbonate.
NH4, CO3. Is that a solid? Or is
No,
it
it's
it's aqueous? Okay, I was about to say is it in water, but yeah, aqueous plus.
Silver nitrate.
Oh. And that's going to go to
Ammonium nitrate, which is
Oh, yeah, I was like, no, a silver carbonate, but sorry, I was doing the other one first.
And then
NH4, NO3. So I did it in a little bit of different order, but yeah, this is what you're going to get. Balancing coefficients, I'm going to need a 2 there and a 2 there. Now, this is the chemical reaction, and we can notice a couple things. Does it ask for a specific things, ions in solution at the end, or does it ask for all ions in solution?
all ions in solution.
So we're going to have to, if we think about this in terms of the total ionic, not the net ionic, but the total ionic, we're going to have 2 NH4 plus CO3, 2 minus, plus 2 Ag plus 2 NO3 minus. So I'm going to need to find 1, 2, 3, 4 ions in solution. I'm going to have the same things over here. Ag2CO3 plus 2 NH4 plus 2 NO3 minus. Now, notice I do have some spectators, right? My ammonium and my nitrate are both spectators. So that means in order to figure out how much of them exists in solution, all I need is their starting concentrations before the reaction occurs. Because whether this reaction occurs, and this is one of the things that's weird about how we represent chemical reactions. When we write this down, it looks like I've got reactants and then I've got products. But keep in mind, this arrow is essentially a time separation, not a space separation. So inside of our beaker, I've got all of the reactants and all of the products present into varying amounts, depending on how much the reaction happens. So when I look at this, if I say the ammonia and the nitrate don't change in the reaction, however much I start with, like I could split them up and say, oh, some of it goes this way, some of it goes that way, but in all actuality, those two are going to stay the same. So I can get those pretty easily. How much ammonium, how much of the NH4CO3 do you start with?
It was 0.25 molar, and it was 5 milliliters.
And how much silver nitrate?
0.3 molar and 6 milliliters.
Wait, it's 50 and 60 milliliters, not 5 and 6. Yeah.
Oh, was it? Oh my
Yeah.
god,
No,
sorry.
no, you're fine. 50,
50? 5 0?
50
50
And
and 60.
60?
Yeah.
Doesn't matter, right? Like 50, 60, 5, 6, 0.5, 0.6. Like the ratio is going to be the same. But let's go ahead and do 50 and 60. 0.25 times 50. Oh, yeah. I like to use millimoles. We won't get into that.
0.0125, I believe. Yeah.
A quarter. Okay. And 0.3 times 0.06 is going to be 0.018. Now, at this point, I can say when the NH4 breaks up, I'm going to have 0.0125 moles of it in a total volume of 110 milliliters. And when the AgNO3 breaks up, I can say I'm going to have 0.018 moles of nitrate. And those aren't going to change. They're gonna just carry through, right? And I'm going to not do it that way. I'm going to do it the stoichiometry way, and we're going to see how it works out. So when we look at this, we say, okay, which one's limiting? 0.018. It's the bigger number, but I need twice as much, and I don't have twice as much. I'm going to start with zeros here. Then I'm going to go ahead and do my reaction. I'm going to do minus 0.018 times a 1 to 2 ratio, minus 0.018 times a 2 to 2 ratio, plus 0.018 times a 1 to 2 ratio, and plus 0.018 times a 2 to 2 ratio. I get my end step 0 because it's the limiting reactant, 0.009 because the 1/2 factor, 0.018 because of the 2 to 2 ratio. 0.0125 minus 0.009 is going to be 0.045? 035. 0035. So when I look at this, I say, okay, this is solid, it's not in solution. I've got 0 carbonate I've got 0 nitrate and 0 silver on my reactant side, so I've got 0.018 on my product side for my nitrate.
Okay.
So my nitrate actually doesn't change. It's just where I'm representing, because keep in mind, all of this is in the same beaker. The difference between start and end is a temporal change. So I had 0.018 nitrate at the start, I have 0.018 nitrate at the end.
Okay, so that's just...
That one's the same.
Oh, okay.
My carbonate goes from 0.018 to nothing, right? It all gets precipitated out. Sorry, not my carbonate, my silver. My silver gets precipitated out.
How do you know?
Because the silver, if I look here, this is my split. Silver is my limiting reactant.
Yeah.
Right, and the silver carbonate is a solid. So there's no silver ions in solution. This was specifically asking about ions in solution. So no ions in solution. Technically, there's a small amount of ions, but that's for Chem 126 again. Right? You do a little bit of equilibrium phenomena, energy balancing in Chem 125. We're not going to worry about that yet. The amount of silver in solution is going to be something like 10 to the minus 12 moles. It's approximately 0. But, so, no silver left in solution. It's all in the precipitate. When I look at my carbonate, I've got 0.0035 moles of carbonate left in solution. When I look at my ammonium left in solution, I've got 0.0035 from my reactants, and I've got 0.018 from my products. And I'm going to subtract those two and get 0.0125. Is that right? No, that's not right. Did I mess up someplace? Oh, hold on. This is weirding me out. I thought I was so clever. I know how much ammonium I should have. Oh, I think I know. I just want to... That calculator doesn't work. Can you hand me that calculator? I think I know what my mental mistake is, and I just want to double check it. That's weird. Okay, where am I messing up? Because I know my ammonium. Oh, okay. Yeah, that's why I'm messing up. The ammonium carbonate was 0.0125 moles, but how many ammoniums per an ammonium carbonate? 2. So I have to take this number and multiply by 2. 0.0035 times 2, so that's 0.018, 0.25, and then you're going to get this number times 2, right? So I made a very Gen Chem mistake, right? So when I look at my amount of NH4 plus, I'm going to have 0.0125 moles of NH4CO3, and I've got a 2 there, and I'm going to have 2 moles NH4 for every 1 mole NH4CO3, 2. So I forgot that factor of 2. Don't forget your factors of 2. So that means I should have 0.025 moles of NH4 plus at the start and at the end, since it's a spectator. 0.0125 times 2 is 0.025, and 0.035 times 2 plus 0.018 is also 0.025. Okay. So it does work out as long as you don't forget your mole ratios.
So the concentration of each ion is just those numbers up there times 2.
No, that's the mole. So all we found at this point is the moles of each thing.
Moles of each thing.
So this is the moles of NH4, the moles of NO3, and no silver left over, and the moles of CO3 left over, right? So then I'm going to have to take each of those number of moles and divide by 0.11. Why am I dividing by 0.11? How do we get molarity from moles? Divide by
Divide by the liters.
Divide by the liters. How many liters of solution do I have if I added 50 to 60? 110. 110 milliliters would be 0.11 liters. So I have to take each of these numbers, divide by 0.11 liters.
Okay.
That will give me a molarity. That will give me a molarity of NH4, and then I can do the same thing for my molarity of carbonate, and I can do the same thing for my molarity of nitrate. And also, I messed up my molarity of nitrate. No, I didn't. It's one nitrate for every silver nitrate. It's a 1-to-1 ratio. Don't let the mole ratio of the molecule with your starting material confuse you with the mole ratio of the reaction. Right? Those are two different things. The molecular ratio versus the chemical reaction mole ratio. Yeah.
If you're trying to, I'm just trying to understand how the 0.0035 times 2 is just 0.07.
Yeah.
Right, and then you add that to 0.018.
Yeah.
And that should give you 0.025.
Yeah.
Why is it? It doesn't do that? Because I'm.
Yeah.
He just wrote it wrong.
Yeah, that's right.
Oh, okay. Oh, it's supposed to be like 0.0175 or something. Because like 0.018 times plus 0.07 is not. Doesn't have a 5 at the end.
0.007.
Oh, it does. You're right. Sorry, my math is wrong.
Yeah. 0.007, not 0.07.
Right.
Yeah.
Why did you get the liters again? Where did you get that from?
50 milliliters plus 60 milliliters.
Okay.
Right? And when we're doing concentration, we need total volume of the solution. So we're going to do 50 plus 60 is 110 milliliters. Divide by 1,000 to get 0.11 liters.
And why'd you divide everything up? Like add everything, like separate the NH4 to and
So
carbonate?
I was trying to show, so I did everything for the blue reaction, that's why I switched back to blue.
Okay.
I wanted to show the total ionic to just essentially show my ammonium
Mhm.
is a spectator, so my concentration at the start should be the concentration at the end.
Okay.
Or my number of moles at the start should be my number of moles at the end. And my nitrate was a spectator. So those two I should expect however many moles I had at the start, how many moles I have at the end.
Got it.
If we don't realize that,
Mhm.
we have to do this extra step of adding things together and figuring out where my ions are.
Okay.
So I'd have to take these amounts in blue and then split them into all of the ions.
Got it.
So this 0.0035 moles is the amount of ammonium carbonate in
Right.
excess.
Mhm.
And then I would have to split that into my moles of ammonium and my moles of carbonate.
Got it. Okay.
This 0 is my amount of silver nitrate left over, so that doesn't matter.
Mhm.
This 0.01009 is my precipitate, so it doesn't matter. This 0.018 is my ammonium nitrate, and I have 1 mole of ammonium for every 1 mole of ammonium nitrate, and so on.
Got it.
After it precipitates out the silver carbonate, do you still have 110 milliliters?
Approximately. Right, so when you start talking about like reactions changing volumes, it gets really kind of nuancy, right? My favorite place to think about this, is it okay if I erase this? Any other questions about this? I'm just going to erase this part in green here so I can show you my favorite kind of like complicated thing for thinking about this. HCl plus NaOH goes to, let's just go arrow, H2O plus NaCl. Is producing that H2O going to change the volume? Why not?
It was already there.
It was already there, right? Same thing with this. The silver nitrate, like the silver ions and the carbonate ions were already there. Now, the catch you get into is, well, you say, okay, silver carbonate ions, and this is getting a little bit beyond what we do in Chem 124, But if you think about a silver ion in solution, a carbonate ion in solution, the ionic attraction to the water dipoles can create some additional density. But then when the silver and the carbonate bond together and create a crystal lattice, that can reduce density. And those tiny fluctuations will cause like microscopic fluctuations in the total volume, but not enough for us to measure on the milliliter scale. We're talking like the microliter to picoliter scale changes in volumes for this stuff. Now there are some weird reactions that you can do that actually like freezing water, right? Freezing water, we see this giant volume change, even though you're not actually doing a reaction. You're just changing the density by changing the crystal structure. So there are some weird places where volume does change, but in most of our reactions, it's negligible. Yeah.
Real quick, on one of the labs online, I have a blank grade, and this is the lab. So if you want to just.
No, this is here. I'm kidding. Give that.
Okay,
I'll add that back in just a moment.
sounds good.
Yeah.
It's unrelated to this.
Okay, are we ready to move on?
Yeah.
Quiz, you ready for it? Okay. Watch the videos, feeling better about it? Great. If you want to put that in the hallway, you can. Ready to move on? Band gap.
And specifically,
So that is where, you know, the Beatles are much better than the Who. There's just a huge gap between them, right? I'm kidding. I don't know if that's actually true. That's pretty subjective. Are the Beatles better than the Who?
Yeah.
better than most everything.
Is that a conductor or an insulator?
Oh.
Oh, how big is, or is it a
Super
semiconductor? No, okay, so band gap.
So the question I have is,
Yeah.
Unless you want to just, okay, the question I have is, I know that as temperature decreases, conductivity increases.
Yes.
Yes. And,
For what materials?
conductors and semiconductors, but not what? No.
That's no, not so much. So when we think about this, so band gap theory essentially says, look, if I've got an atom, it's got like some s orbital and some p orbital, or like d orbitals mostly if we're thinking like iron or something like that. If I've got two atoms next to each other, and there's some gap between those, right? If I've got two atoms next to each other, I get like 2 lines. If I get 3 atoms next to each other, I get 3 lines. If I got like a trillion atoms next to each other, I've got like a trillion lines that are all so close to each other that it just looks like a giant smear. We go from having discrete levels to having pretty much a continuous energy distribution. But I still end up with a gap. This would be an insulator. And then if I had a semiconductor, I'm just going to do like this for like representing it because time. There's my like highest, and then that's like a semi. And then for a conductor, it's pretty much here's the highest, and then here's right total overlap. Now this is a relatively cartoonish picture, but again, like most of the things we've done in general chemistry, this cartoonish picture gets us most of the answer without doing much of the work. Like these types of calculations for actually calculating energy gaps from like first principles quantum mechanics, really difficult to do quantum mechanical calculations in condensed phases, like when you've got like solids or like liquids, because you've got so many interactions that you need to keep track of. Right, and especially when you're dealing with large crystalline solids where you're dealing with like thousands of atoms, you've got a wave function for every electron. So even like iron has what, like 27 electrons each? So even like 10 iron atoms, and you're looking at like 270 wave functions, where each wave function has 3 to 4 quantum numbers. So you're looking at like, you know, like hundreds of variables. You're looking at like 800 variables for just like 10 atoms. And we want to do it for like 1,000.
Right.
So it becomes really difficult to actually do that. So this gives us a pretty good idea of what's going on. The problem is there's physical difference between these, right? So when I look at a conductor, since my valence band and my conduction band are already overlapping, adding additional energy to try and get over that gap doesn't help at all, right? So heating up a conductor kind of messes it up because I'm not getting any jumping energy benefit and just making the atoms. So the cartoonish kind of argument for this is heating it up will make the atoms wiggle more, which will essentially make the electrons have a harder time getting through the material. So like that's the cartoonish kind of explanation for it. When you go to a semiconductor, because there's a little gap here, the thermal energy actually helps the electrons get to the conduction band. Right? So that extra energy, because I need to jump, that extra energy actually helps the electrons get to the conduction band, and heating up a semiconductor actually makes it conduct better.
Okay, so in a sense, you can think of it as if the energy gap is decreasing when you heat it up because it's supplying more energy, like relatively.
Yes, however, heating it up is not likely going to change the energy of the gap. It's changing the energy of the electrons.
Okay.
Right? And that's a subtle difference. The reason I was like, ooh, is because if you heat it up and the atoms start to vibrate more, if the distance between them is on average smaller, you could make your gap larger. Or if the distance between them on average is larger, you could be shrinking your gap. There could be some thermal effects, but I've never seen somebody actually talk about the thermal effects in semiconductors like that.
Okay.
They usually just talk about the kinetic energy being provided to the electrons. Now I want to go heat up a semiconductor and see how much the gap changes.
Could you use a semiconductor as like an insulator, like a partial insulator?
A really terrible one.
Yeah.
Right?
Uh-huh.
So depending on the semiconductor you use, you get different levels of insulation.
Mm-hmm.
Even an insulator, at some point you're going to break your insulator. Right? If you provide enough energy, you can do this. My favorite example of breaking an insulator, lightning. If you think of the ground as one level and the clouds as another level, you build up enough energy in one, you can arc across it. Dielectric breakdown of air. Yeah.
So increasing the temperature in an insulator wouldn't really matter because is that
correct, right? An insulator, increasing the temperature, usually in order to get conduction in an insulator, you heat it, you'd have to get to temperatures where you're actually going to be breaking down the material before you get conductivity.
Okay.
So you get that kind of breakdown of material if you heat it before you get, look, if you've got a good insulator.
like melting plastic?
Yeah, exactly, right? So a lot of the insulators we use for making like plate capacitors and stuff like that are these weird plastic materials and these weird different materials. Some place where that might not be true is if you do like diamond, if you do like rubies are great insulators, and they have huge dielectric constants. So you can get these different things where you can like actually heat them up a lot and not get dielectric breakdown and not break down the materials. But again, like usually when you make a material that's a better insulator, it also takes like the gap grows larger and then it takes more thermal energy to break it down. You get this kind of trade-off. So with insulators, the temperature usually doesn't matter until you're breaking down the material. Yeah.
So heat is worse for semiconductors when it comes to moving electrons. Better.
What do you mean by worse?
It lowers the energy. Cause I know when you increase the temperature for semiconductors, it increases the energy because they're able to jump the band gap.
More than we say it increases the energy, because increasing the temperature in all of these cases increases the kinetic energy.
Yeah.
Right? The thing that's important in semiconductors is increasing the kinetic energy of the electrons increases the conductivity by letting it jump the gap better, more easily, providing energy to help it jump the gap.
Okay, so how does temperature affect conductors and insulators?
Insulators, it doesn't really affect it because the gap is so large, the thermal fluctuations is not enough to have a big impact. For conductors, increasing the temperature actually will decrease conductivity, and decreasing the temperature will increase. So we see this opposite effect because we're looking at two different phenomena. Here we're looking at the kinetic energy provided to the electrons, and the fluctuation in the nuclei is relatively minimal. Here, since the gap is already gone, what really matters is the kinetic energy of the nuclei, right? So it's like it's electron versus nucleus, and so we see opposite effects in those two.
So basically, in a conductor, the electrons will have more difficulty navigating the orbitals. Is that when you heat it up?
That's the cartoon argument, yeah, right. And
Is that a valid argument for the test?
yes, that's a valid argument for the test, right? Like that is like again just like Vesper works on the test. Like that is Vesper, as far as I'm concerned, is a cartoon argument, right? It's like, oh, things just push away, and it works. It's classical. But when you want to get down to like the kind of like the electric potential map as you change temperature is what we really want to look at. Like you can think of, wow, how many of you like space? You know, okay, oh, great, okay. So you know how when you talk about like gravitational wells, you can talk about like Earth as having a gravity well, and as something goes around, it kind of gets caught in that well. We can actually do the same type of picture for nuclei creating, instead of a gravitational well, creating an electromagnetic well that electrons can get caught in and try and and you call that like the electric potential map. Like, so you can kind of create this contoured space that the electrons have to traverse in an energetic sense, not a spatial sense. Which is why that cartoon argument doesn't work, because the cartoon argument is like the electrons trying to get down a hallway. And it's like almost true if you look at it on this energetic sense. And if the atoms are all moving, if the nuclei are all moving, then that potential map is fluctuating, and that can cause the electrons to get trapped in different places for a moment as it's trying to traverse that. It's very like, the problem with talking about anything with temperature is it's dynamic, right? And the problems we have with all of these things is we're trying to do this static representation. But the cartoon argument is good enough for this. Other questions?
I have a really quick one as well. Okay. On one of the worksheets, it asked about like what kind of intramolecular bonding is like broken. Oh, I can get it. You know what I'm talking about?
Yeah.
Where it was like what kind of intramolecular bonding is broken because the IMF of water. So like when you put a material in water.
Here it is. So it says typically the IMFs of water with other molecules is not strong enough to break. Lattice energy, covalent bonds, ionic bonds, or metallic bonds.
And I was thinking it's both covalent and metallic.
Yeah.
Also, it's
multiple
choice though.
Oh yeah. So that's a mistake. So you know how I like to do these really horrible multiple choice problems where I'm like 1, 2, 3, 4. I switched it to something like that, and then A is like 1 and 2. B is like 1, 2, 3. C is like 1, 4. D is like 3 and 4. Sure.
Okay. So the answer would be both
covalent and metallic.
Will you read it again? Typically, the IMFs of water with other molecules is not strong enough to break. A, lattice energy, B, covalent bonds, C, ionic bonds, and D, metallic bonds.
Did they even break lattice energy? That was like you can't break lattice energy.
It can overcome lattice energy to dissolve
the metallic bond. Or sorry, the ionic bond.
the ionic bond. Yes, in some cases, but not all cases. So that's where we have to look at our solubility rules.
So, right, like, didn't we go over in lecture that like sugar, like the actual like C6H12O6 won't be broken, but the lattice structure will be?
Yes,
Okay.
exactly. Because does sugar dissolve in water?
Yes.
Do we break covalent bonds in water?
No.
Typically no. Acids we do, but typically no. So yeah, you're correct.
Okay.
Yeah.
Do we break bases in water?
Our strong bases, yes.
Okay.
But our strong bases are ionic bonds anyway,
Okay.
right? They're all the hydroxide salts.
And the weak bases, is it negligible?
Weak bases do something different.
Does it do like an equilibrium thing where they go back and forth?
And it's weak bases. So again, Chem 126 ideas.
Yeah.
But most of the weak bases we talk about are amine groups that are proton acceptors. So we have to change our definition of how bases behave in order to define weak bases.
Like different definition of acid base.
Yeah. We get into that later if you want to take Chem 126, which I encourage all of you to take. It's a great class. Crickets. Okay, other questions?
Quantum numbers, is that fair game for this midterm, or was that more last midterm?
That was more last midterm, but the S&P orbitals came back, right? So when we
Yeah.
talk about hybrid, so there are some places where we still need to know some of the stuff about those quantum numbers.
Okay.
Um,
But not like, we don't have to like find the.
generally
numbers
no,
for it.
but a little bit could be on there,
Okay.
right? Yeah.
So would you say that to the extent this midterm is cumulative, like there's not gonna be something from last midterm that would be like one of the big free response questions
Correct.
in depth, but it might be
Yeah.
like involved in multiple choice question or involved
Yeah,
in
and it could be
it's
like
not focused on it.
yeah. So the way I put it is I'm emphasizing the new material.
Okay, that's fair.
I'm emphasizing the new material.
Yeah.
Anything that I haven't tested you on before, that's what I want to try to get on. But I love bringing in like showing the connectivity of concepts.
Yeah.
So
So wait, is there an answer key for the homework 6 or something?
no,
I don't know where.
I don't have any answer keys for anything.
I don't want you to.
Could you make a quick chart real quick of like SP, like comparing like the SP like things to like trigonal planar and like or like the geometry?
I mean, you can.
Yeah. So wait. So SP is linear. SP2 is trigonal planar.
Uh-huh.
And SP3 is tetrahedral.
Yep.
Okay.
Great. Okay.
Thank you. But does that apply only to its geometric shape or also?
That's mostly for its electronic shape,
Oh, okay.
right? Because when we're looking at Vesper to get our geometry, we include the lone pairs. So you want to know an answer on homework 6?
Well, I don't know where, because I don't know if I'm messing up any of
Okay, well I can take a look at that. We can stop the
Okay.
video. I can look over your work.
Okay.
You can also ask other people, but yeah, like I don't provide answer keys because it robs you all the joy of figuring it out. Because the problem is, how many times have you been like, I don't know how to do this problem, and as soon as I started, you're like, oh yeah, of course, right? So having answer keys, like the most difficult thing in a problem is figuring out where to start and being able to estimate whether you're correct or not. And if I give you answer keys, it kind of shortcuts both of those things that are the most difficult things you need to work on. And if I give you an answer key, like especially if it's where it's like it's worked out, like it's just it robs you of like the most important cognitive capability of thinking through the problem. So I don't provide answer keys. But I can still look at your work and we can figure out what's going right now. Yeah.
On the Lewis structure worksheet, if I'm remembering correctly, it would ask for like draw a Lewis structure or something, and then the geometric shape, the
electronic shape,
right, and then that's all.
hybrid orbital.
Yeah, that part, the hybrid orbital part.
For the central atom.
Yeah, like can you go over what?
You just did.
That's what that is.
Yeah. SP,
So you just look
SP2,
at the
SP3.
shape, and then it's obviously either SP, SP2.
Yeah, and I talked about this earlier in the video. You can go look at it. But hybrid orbitals have this big flaw of you can't figure out the hybrid orbital without knowing the geometry or the bonding pattern. But if you have either of those pieces of information, so there's essentially 3 pieces of information, and if you have any one of the 3, you can figure out the other. If you know the bonding, or if you know the hybrid, or if you know the geometry.
Oh, it also, that's what it was. It asks for oxidation too.
Oh, oxidation is
Yeah.
a whole different thing.
Is that something that we need to know?
Yeah.
Okay, can we go over that?
That's how you get like, do you have an example?
I can whip one out.
Yeah.
Wait, I have a question.
Sure.
For hybridization, you look at the electronic geometry, right? So like
Yes.
not the blockade. Okay.
Yeah.
So bent would still be SP2.
Well, depends on what kind of bent.
Depends on what kind of bent it is.
1, 2 valence, like 2, 3.
Okay.
So you've got
Regular.
2 bonds and 2 lone pairs.
No, 1 lone pair, 2 bonds.
That would be SP2. Yeah.
Okay.
Because you've got 3 things attached. Lone pair, bond, bond. So SPP.
So that's in with the Bill's tetrahedral.
Oh, orbital hybridization.
I'm gonna erase this.
There's a question on one of the worksheets I asked about oxidation.
Oh, for sure.
Yeah.
How else do you do, what's it called? Redox reactions, thank you. Man, are office hours almost over? I'm just realizing my brain is like slowing down. 4 minutes, okay.
Okay. What is the oxidation state of chromium and chromium or chromate?
What's chromate?
CrO42 minus.
So, let's go ahead. I don't know if I've done any of these in the mathematical sense. What's the charge on oxygen?
Minus 2.
How many oxygens are there?
4.
What charge do I want left over?
Minus 2.
What must be the charge of chromium?
6.
Done.
Oh, so oxidation state is charged?
Yeah.
So when something oxidizes.
So this is again like one of the things I mentioned, like the vocabulary we use becomes really important. So the reason they call it oxidation state is again a historical kind of context. They used to understand the charge on all atoms based on how many oxygens they could get it to react with. So oxidation state and charge are synonymous.
So when something oxidizes, it loses electrons, correct?
Yes, oxidation involves loss.
And then reduction implies gaining.
Yes.
Okay, that's a weird. Reduction's like less, but okay.
Okay. Yeah, and again, that comes back to the historic, like
yeah.
they defined it in terms of oxygen instead of in terms of electrons originally.
Got it.
So kind of flip things. Okay, I'm gonna go ahead and stop this video.